Okay, the chirality of carbohydrates. Here's a lot of terms here. Now it turns out that if you have a molecule and you build a molecule that looks like its mirror image and you can't overlap them completely, then the molecule is chiral. And that chirality is really important for a lot of reasons, and especially in biochemistry, and we'll get to that. But right now, we just have to determine if a molecule can be considered chiral. And we can look at its structure and determine that. If we can find a carbon that is connected to 4 different things, so didn't want to use C here, so 4 different branches off of that carbon, then it is chiral. And we can either put an asterisk, that tells us we're dealing with a chiral carbon or chiral center, or we can just say the molecule is chiral. Now here, notice this carbon has 3 hydrogens on it. Well, there's 3 of the same thing, so that can't be chiral. Here's 2 hydrogens here. They're they're not. This carbon is connected to 2 of the same thing, so that can't be chiral. Look at this carbon though; it has a methyl group, a hydrogen, this ethyl branch, and then this whole thing here. So you have to look at all 4 branches. So that would be chiral, or a chiral center. 2 hydrogens here. Anytime you see a CH2 stop or CH3, that can't be a chiral center. Same here, here, and here. Those can't. How about this carbon? It has a hydrogen, has a methyl group, has an ethyl group. Don't just look at that it's connected to a carbon. Look at the whole thing. We have a methyl, ethyl, and then this huge branch here. So that's a chiral center as well. We have a ring here. A ring is same kind of thing. You just got to be careful. This isn't a chiral center because it has 3 of the same thing. This can't be. This one can't be. Now, how about this carbon? Well, it has a methyl group. Then it has the ring going in this direction, and then this direction. But notice this carbon has 2 hydrogens. This carbon has a fluorine, and it has a hydrogen there. So that's 4 different branches. This carbon has 4 different things attached to it. Think of, even if you go all the way around the ring, think of it as 1 branch this way and then 1 branch this way. And so this can't be because it has 2 hydrogens here. This carbon, there's no other chlorines in the molecule, so you'd assume that would be chiral. And yep, that's it. I got the 3. Now here is it from here's a line angle drawing. Okay, so the endings are CH3, so these are out. The kinks are out. Now here we have a carbon. We don't normally draw the hydrogen. Notice a methyl group, a chlorine, a hydrogen, and this whole branch. So this is chiral. How about here? This has a hydrogen, a methyl, an ethyl, and then this thing here. So definitely chiral there. And then what's going to interest us most are going to be these monosaccharides. Now, let me draw out the hydrogen here. See, carbon is bonded twice to the oxygen. You consider those to be separate bonds. So it's bonded twice to the same thing. Literally the same thing this time. It's not just 2 of the same atom. It's the same atom that's bonded to twice. Then now look at this carbon. It has a hydrogen and oxygen, this branch here, and then this completely different branch here. So that's chiral. And the thing about these are these Fisher projections that we'll be looking at down the line. But anytime you have this cross like this intersection, those are chiral. You can see that each one, even here where you have a carbon, hydrogen and oxygen, looks like it's the same thing in either direction, but then they end in a different way. So this whole branch is different from this branch. And that's it.